Hello? Okay, welcome. Hello? We are here today, Jiří, Šilha, forgive me for saying bad your name, of course. Here, his PhD at the Comenius University in Bratislava in 2012. During his PhD study, he spent 6 months at the NASA Orbital Debris Office at Johnson Space Center, and during his internship, she participated at the observation campaign performed with the 6.5 Magellan telescope situated in Las Campanas Observatory, Chile, and with NASA 0.6 meters modest telescope situated at Cerro Tololo, Chile. Between years 2013 and 2017, he was a researcher at the Astronomical Institute of University of Bern, Switzerland, and the main duties cover ESA projects managed and were related to space surveillance and tracking, SST. Currently, Jiří is a research associate at the Faculty of Mathematics, Physics and Informatics Comenius University in Bratislava since April 2019, and he's responsible for the observation program of the 70 centimeters Newton telescope placed at the Astronomical and Geophysical Observatory in Modra, Slovakia. It's data planning, acquisition and processing. He's involved in software development related to image processing, and he's a manager of a currently running ISAPEX study. So you can start.
Thank you very much for the introduction. Good morning, thank you for coming. So as was mentioned, my name is Jiří Šilha. I am from the Division of Astronomy and Astrophysics of the Faculty of Mathematics, Physics and Informatics of the Comenius University, which is in Bratislava, Slovakia. Today I would like to talk about the space debris research we do in Slovakia, especially in the university, but before that I would like to introduce you to our department. I would talk about some other activities or other optical instruments and other research which is performed at our institute, that you have a rough idea what we are doing. Then I move to the introduction and general overview of the space debris issue that we understand, all the terminology and the motivation behind the space debris research, and then I will move to the research we are actually doing and to the projects we are doing. So our institute is quite small comparing to ISU. We have in total 10 researchers which are focusing on different science from meteors through minor planets, photometry and astrometry to space debris and galactic astrophysics. We have also our own observatory. It's called Astronomical and Geophysical Observatory in Modra. Acronym is AGO. The MPSC number is 118. We have there one supporting engineer and 2 technicians. We are actually crucial for the hardware development we are performing at the observatory. So now I move to the instrumentation. This is just the list. I will go deeper to each instrument in the next slides, but just a rough list. So we have a 70 centimeter Newton telescope. This is the largest one optical system we have at observatory. This is dedicated to the space debris. I will talk about it in the second half of the talk. We have the 60 centimeter telescope. It's a ZEISS telescope, and it's dedicated to minor planets photometry. Then we have an all-sky meteor detection system called AMOS, which is a global network of all-sky system cameras, and we have these cameras always paired with the AMOS SPEC, which is a spectral camera which is measuring the meteor spectrum. So I will go from the AMOS, the smallest system. AMOS was fully developed at our institute. The hardware was developed with collaboration with our observatory staff. You can see that the prototype of AMOS, the optical system, on the right upper part. This was the configuration from 2007-08. Now you can see more elegant configuration, which is plotted here. This is the AMOS situated in Chile, and the optical system is in the middle, and the whole, this housing is the protecting one, which is fully automated. It responds to the weather, rain, day, night, and so on. So this was also developed with, at our institute. Maybe what is important is that mention that system AMOS was using commercial software or free software, but it was not our own for detection and orbit determination. But now we moved to our own developed software also for the image detection, image reduction, and orbit determination. So the development not only of the hardware but also of the software of the system AMOS is fully under our control. So we have the full control of the quality of the products. In the end, we understand the errors, where they are coming from, when they're coming from the measurements. So as I mentioned, AMOS is a global network. We have several AMOS cameras in Slovakia, 2 cameras here in Chile, 1 in Teide and 1 in La Palma. There is also 1 spectral camera. Then we have 2 cameras in Chile, also accompanied with 1 spectral camera. And then we have 2 cameras on Hawaii. Again, there is 1 spectral camera. So every time we capture a meteor, not every time, but for quite large part of the population we capture, detect, we can get the trajectory, but also the chemical composition of the meteorite. We are planning to expand the network in the next 2 years to Australia, Western Australia, and South Africa. So this is how the system looks like in different locations. As I mentioned, the spectral camera is always with the AMOS. On the left, here is a AGO observatory camera. You can see the 2 cameras which are here at the Canary Islands, and on the left you can see camera installed in Chile, or the configuration installed in Chile. Here is a composite image from Chilean camera, which is a composition of I think 60 seconds. So we have a video, right now we have a video tracking, so we always track video. I think the cadence or the frequency is 20 images per second. So you have probably like 600 images stuck here. So now I move on to a bigger system. It's also the oldest one we have in observatory. It's almost 100 years old. Is this one? It's a 60 centimeter with focal length of 3.3 meter. It is basically or mostly used for minor planets photometry. In the past, we did it in the cooperation with the Astronomical Institute of the Czech Academy of Sciences, in cooperation with the team of Dr. Pravec. But now we are more focusing on our own projects. I will talk about it in the next slide. This system is equipped with the CCD camera Apogee 8 with 1K by 1K pixels size, and the resulting field of view is 25 by 25 arc minutes. So the primary goal right now is to do photometry of main belt asteroids with focus on Vesta family. Our colleague Dr. Adrian Gallagher is responsible for this photometric program. They are focusing on V-type asteroids, and they are investigating if there is any link between the V-type and the Vesta family. They are looking for possible origin of Vesta, and there are several theories. There is one basic theory which is saying that the V-type can actually belong to Vesta, and it was created through two massive collisions which probably happened 1 to 2 billion years ago. You can see the Vesta population on the right when you look at the figure where it's plotted semi-major axis compared to the sign of inclination, orbital inclination. So the red dots represent the targets my colleagues were observing last years. This population is not well known, and my colleagues are focusing usually on acquiring light curve and to identify the rotational period, and also, of course, if the object is a binary or a multiple system. There are several studies which already were conducted concerning the photometry to Vesta objects. So here are some technical details. Colleagues are focusing on the objects with magnitude above, fainter than 60.5 in visual band, and we don't use any filter at the 60 centimeter, and the accuracy, resulting accuracy of the data points is roughly 5/100th of magnitude. Annually, we are able to acquire 20 objects, and you can see one light curve on the right for object 1998 HG153, which was acquired by AGO 760, and it was also processed by our own tool which we have in-house. On the upper figure, you can see the angular rates or spin rates which were acquired for all the objects we observed so far. Currently, my colleagues are extending their work to NIA objects, and of course the research is still continuing, and they are still open. They are open for possible collaboration in this area. So now I move to the third part of my talk, to the second part of my talk, which is space debris, the general introduction, that you have a good overview why we are doing this and what it is. So when we talk about space debris, we talk about everything which was created by human activity and is orbiting around the Earth, so it's on geocentric orbit, and doesn't have any other purpose. The definition can be problematic, but this is pretty much it. And they can be different type of objects. They're very heterogeneous. We start with the biggest ones, which are few tons spacecraft, which they are not functional anymore. They can be decommissioned intentionally, or they can just malfunction. So this happens quite often. And these objects are usually, for example, this is an Astra satellite, which has a wingspan span of a few, I think it's dozens of meters. Another example of a not functional spacecraft, or in this case probe, was Phobos Grunt. It was a probe supposed to go to Mars to do observations of Phobos or study the Phobos moon, but it failed to leave the LEO orbit, so it stayed at the LEO and eventually it burned in the atmosphere. There is possibility that some part of the probe actually also ended up in the ocean. So there is a second big population, which is more shape-like cylindrical objects, which are upper stages. You can see delta upper stage, which is used quite often, and you can see, for example, Apollo third stage. These lunar mission upper stages are quite interesting in sense, dynamical point of view, because once there was a lunar mission, these upper stages were usually captured by the lunar gravity, but eventually the perturbations from the Earth caused that the objects were actually thrown outside to the heliocentric orbit, and from time to time these objects actually got recaptured again by Earth, and then astronomers are getting a little bit confused. So you have to perform spectroscopy, photometry, and dynamics integration in the time, backwards in time, to actually identify that the object is not really natural, but is artificial from some specific space mission. So once these objects fragment, they can explode, right? Either there is a collision or there is a malfunction on board. You got the fragments. So these fragments can have can be from different materials. It can be aluminum alloy. It can be glass from solar panels. It can be MLI, multi-layer insulation, very thin foils, which are very highly reflective. There are also some exhaustions from the propulsion, and there are objects which are quite having strange origin, which is really related to private sector being active in space. For example, sometimes when you test your upper stage, you have to put a dead weight. So the object which is on the upper stage doesn't have any meaning. The only purpose of the object is just to simulate the weight, that the rocket body upper stage is not empty when it's lifting off. On the upper figure, you can see commercial human star. I think it was an object was supposed to just to advertise the company, nothing else. So when we talk about space debris and its distribution, you can see here simulation of one day, how the dynamics of the whole population is a snapshot is a video of 24 hours from 2008. We use data from public catalog space track, which is provided by United Air Force, to render this animation. And you can see there are several different bulges or dense parts. We can start with the most dense, which is here in the middle. This is so-called low Earth orbit. It's usually these orbits are usually objects up to 1,500 kilometers above the Earth's surface. This is the most dense orbit for several reasons. One is the area itself of the volume is very small, but also it's very used for satellites operation, because it's the cheapest solution to actually put it on 800 kilometers, and it will operate for 20 years. You can even, in the past, you could even service the satellite this way. It's also dense because there was a lot of fragmentations happen in that region. So roughly 80% of all objects are actually, which we track, United States Air Force is actually on this region. Then we have a very unique region, which is this ring. You all probably know it. It's a geosynchronous Earth orbit. This orbit is unique because it's one sidereal period is equal to one rotation period of the Earth. So the object appears to be on the same spot on the skies, or vice versa. The object is always above the same point above the Earth. But once the object is not functional anymore, it starts to drift. It can drift east-west, but also north-south. And then this ring is created around the G-ring. The width of the ring is 15 degrees, and it's caused by the perturbations, gravitational perturbations from the moon. So this is the categorization of the orbits. We have also orbits in the middle. Those are usually highly eccentric, but we have also circular ones. The eccentric are, for example, geosynchronous transfer orbits. Those are responsible for getting the object from LEO to GEO orbit, which means the apogee is in GEO and the perigee is on LEO, is crossing LEO. We have also eccentric orbits like Molniya, which is Russian satellites, and we have really circular orbits with roughly 12 hours orbital period. These are the objects which are used for navigational systems like GPS or GLONASS. So this was the spatial distribution. Now we can talk about how this population is actually growing, or how it's larger or getting smaller. You can see this figure, which was taken from NASA Orbital Debris Quarantary News, I think from issue from this year. You can see what was the status of the population on Earth orbit to 2018. There are different population plotted. For example, you can see fragmentation debris is with this violet color, spacecraft, blue color, functional and non-functional, they are together, mission-related or rocket bodies. So some populations we can actually limit, right? So for example, mission-related, you can really work with engineers to make sure that there is not too much debris released during the launch. Then you can also make some arrangements concerning the upper stages and with spacecraft. But with spacecraft, we see we got some increase. This is due to the private sector is entering this business of satellite having on orbit more and more. Then we have two huge spikes in 2017 is over here, and 2009 is over here. Those are two spikes which were created by fragmentation of satellites. In this case, it was an intentional anti-satellite test which shut down meteorological Chinese satellite in 2007. The object was roughly around 850 kilometers above the surface. So it was created, there were created about 3,000 fragments from this event. And then we have an accidental collision between functional Iridium-33 satellite and non-functional telecommunication military satellite Cosmos in 2009 about Serbia, about North Pole. And during this event, I think 2,500 objects were created. Some of them already re-entered the atmosphere, of course, but some of them will be orbiting orbit for several decades, centuries. You can see that we have also some decrease in the population size. So this is caused by the natural effect of atmospheric drag. So thanks to the atmosphere, we can actually clean the population of space debris to a certain level. We don't do it, actually, it does nature for us. But this source is kind of also limited because it only, if you have an object on 500 kilometers, fine, it will survive for up to 10, 15, 20 years, depends on solar activity as well. But once you are on 1,000, 1,500, there is no, the atmospheric drag doesn't play a role in the dynamics of the object anymore. So the population is still growing, but we could have some hope when we look at the atmospheric drag, but we know that the whole infrastructure will change rapidly in next months, years, and that's because of the new satellite configurations called mega constellations. Mega constellations it's a constellation of thousands of satellites which will be surrounding the Earth, orbiting the Earth, or different orbits. And the idea is that if every point on the Earth, you will, in every time, have a broadband internet connection. So this is the private company's initiative. There are several big companies which are really involved in this, and there will be several constellations launching or being operational soon in next 12 months or new years. Originally, the idea was to put this population to less dense altitudes, like 11 to 1,300 kilometers. You can see we already really got crowded this part, so it will be, I'm responsible to really put more density on this region and create the probability of collisions too high. So this means that once we have these populations up, we can have a constellations up to 12,000 objects per constellations. Even 1%, if the 1% of these objects will fail, which always, as I said, happens, we have like 120 objects, let's say, per year. We have 120 objects per year, new space debris, just from the constellations. Not even mentioning the whole traffic will change. So you have to set up the old satellites in the orbit and new satellites up to orbit. So this will strongly also influence the whole dynamic of this orbital debris around the Earth. So the motivations from the motivation to do actually to observe orbit debris and do further research is to protect the satellite infrastructure which is already placed or it will be placed in the future. And of course, the mission-related space missions with the human involved is also is the highest priority for space debris, protecting against the space debris. So when we look at the research topics, this is the list of, let's say, talks or sessions which were at the European Space Debris Conference, which took place in Darmstadt, Germany in 2017. So what is the space debris community discussing all the time? Of course, the observations, they provide information to everything which will be below. Then we have a space surveillance and cataloging. So when you want to do space surveillance, you have to have a network of sensors. You have to optimize the communication between the sensors. You have to optimize the observation strategy that you are as efficient as possible. So this requires some mathematical models and so on. You have orbit determination and prediction. You have to have as best as possible the model, how to calculate the orbit of the object. You have to include all the relevant perturbations which can influence the dynamics. Attitude determination and prediction. When you would like to remove the object, you need to know how the object behaves, how it will behave in 10 years. So this is the topic of this session. Or orbit fragmentation helps us to understand why the fragmentation happened or where it happened, what could be the parent body, how many objects were created, where the population will actually expand in the future, the dynamics, how the orbits will change in the future. Debris environment modeling, this is connected to the fragmentation. So sometimes you have very small particles, so you have to model these small ones by using some statistical information from radars or in situ measurements. And this way you can actually predict which, for example, inclinations are very dangerous for spacecraft to be on. And then we have a service like operational collision avoidance, which is crucial to space infrastructure. Re-entry analysis, where we are concerned that the object actually can re-enter, survive the re-entry, and actually go down to the ground. Then it can hurt some population, or it can contaminate the local area. Then we have a hypervelocity impacts and shielding, which help us to protect against space debris impacts on space. So you want to improve your shielding for ISS or your spacecraft. And there is a debris mitigation activity removal. This is more engineering approach when you try to figure it out how you would actually capture such an object and remove it to actually stabilize the whole population. So when we talk about observational techniques, I will just go briefly through this slide. Of course, we have optical ones. This is what we are talking about here. So it's an optical passive. ESA is often referring to it. The reason is because there is a new one and now also entering the space debris research and tracking, and these are satellite laser ranging. These stations, which are operating SLR, using SLR, are able to actually track debris if they are strong enough, and they can be complementary, or they can take over some of the objects that optical telescopes can track. When we talk about SLR, we usually talk about LEO orbits up to some medium orbits, up to GNSS, GLONASS, GPS, and so on. Of course, we have radars. Radars help us a lot to observe objects on low Earth orbit. So without radars, we would have to have an extensive network of optical, passive, and SLR sensors around the whole world to be able to actually track it. With the radar, you have a very good wide field of view. You can do survey, you can do tracking, you can combine. So they are really essential for LEO. But once you go higher, the signal is getting much, much weaker, so you have to move to optical passive. For GEO, there's only optical passive possible to use. And in situ measurements, they are also used, but they are more for statistics. You cannot really use them for real-time tracking and so on. So those are the technical observation techniques we can use. So I will talk about the optical observations, the passive observations. So what do we do when once you have a telescope? You can do survey. So you have to discover objects to actually have a catalog and then do research. So we have some catalogs available, of course, but there are many teams around the world which are doing surveys. They discover objects, they do initial orbit determination, and then they do a follow-up observations, improve the orbit, and they catalog the object. You can do it by using astrometry, of course, when you do the follow-up. So astrometry helps you not only to measure the objects comparing to the star background, but also it can help you to validate your system. So if we talk about, when we are talking about the space debris, right, they are moving very fast. On GEO, it's like 50 arc seconds per second, but when we go to LEO, we're talking about degrees per second. So even 10 millisecond error in your measurement or noise can cause enormous error in your astrometric data. And this consequently leads to meters, hundreds of meters, maybe even kilometers of error for a prediction of the object. This is essential for conjunction analysis and tracking with SLR, for example. So you can use astrometry data actually to calibrate your system and see if it behaves properly over time. Then what we do is photometry to acquire light curves. Light curves have a strong information in them. You can actually, of course, obtain information like rotation period. You can, with some assumption, also estimate the attitude state, exact attitude state, like rotation axis direction in the inertial system. And of course, you can also monitor the period or rotation period over time, how it behaves. This can tell you then, for example, this is applicable for active debris removal missions, but also once the object suddenly starts to spin or decelerate, this is really a strong sign that something is terribly wrong with the object. Either there is something internal wrong, there could be some leakage of the fuel, or there is a kind of collision happen which could disintegrate the object and lead to a possible fragmentation in few orbital revolutions. So, and then we have a reconstructed phase function when you put the light curve together, and this can tell you something more about the shape of the object, reflectivity properties, you can have a specular reflections and so on. And you can then also do identification of the object when you see, oh, I see this pattern before, and you can identify the object according to it. Then we have colors or BVR photometry when we acquire color indices for the object. So we acquire, due to photometry, different colors, different filters, excuse me, and we can actually investigate deeper the surface properties. You can extract probably albedo from this type of observations of the object, and so on. Then we have a reflectance spectroscopy, which help us when we actually measure the spectra of the solar light reflected from the surface. So it's similar like the photometry colors, but much more accurate, which can give you the information about the surface and possible origin of the object. So, and then we have a spectroscopy. This is used very uniquely when you have a re-entry of artificial object and you observe it with spectroscopy. Actually, you can see or you can monitor which part of the object is actually burning at that moment in the atmosphere. So, and now I'm slowly moving to the Argo 70 centimeter. This is the reason why actually what I'm actually working on now. Argo 70 centimeter is a Newton design. We can secondary mirror here. You can see primary parabolic 70 centimeter mirror here. It's from Alumna Optics, it's good quality. And this is the configuration when we were installing the system. This is already when it was put together. This 70 centimeter was built by an Austrian amateur astronomer who is very enthusiastic, and he's building his own stuff. And he got bored with this piece because he wants to be even bigger in his workshop. So our university purchased it in 2015, and we installed it in 2016 with the goal to primarily use it for space debris research, but it's not only to do observations, also to do development on the system. And this is secured thanks to the ESA PEX fundings, which we had so far two. One started in 2016 and ended in the fall last year. I was the manager of this project together with my colleague Jiří. And now we started a new project in the spring, which will be focused on space debris tracking on LEO. So we will extend the geo, astrometry, photometry, and GNSS, astrometry, photometry to LEO, to support, for example, also SLR stations to the tracking of the debris on LEO. These activities cover a lot of topics. So we have telescope control unit development, we have hardware development for the dome, we have interfaces development, we have software, image processing software development. I will try to talk about it in the end. And we don't do orbit improvement, but our colleagues, our partners will do both. In the second activity, we have partners in Switzerland, which is Astronomical Institute of University of Bern. They have their own system, 1 meter SIMLAT telescope, which is a hybrid between laser station and optical system. And then we have a Graz SLR station, which is operated by Austrian Academy of Sciences, which is the first one, or is the leader in the space debris tracking with SLR systems. And these both groups are actually capable also to orbit improvement and determination. So we provide them data, they do the tracking, and then we, together with the angle measurements and range measurements, we can come up with the orbits improved TLE predictions and provide them to other SLR systems. Maybe more to the technical details of the 70 centimeter. It's an equatorial mount. You can probably now it's a Newton. You can see that we have a CCD 1K by 1K size. The resulting field of view for 1 pixel is 1.7 arc seconds, and the field of view is 29 arc minutes by 21 arc minutes. So maybe just to make sure that it's clear what the ESA PEGS means, Slovakia is not an ESA. So how we can actually have a project? There is an initiative called ESA Plan for European Cooperating States, PEGS, which helps candidates to be ESA members to improve to a certain level, and they also support us from management perspective, but also they help us with some technical advice. The funding goes from the government, Slovak government, through the ESA to the Slovakian companies and institutions. Since the beginning, from 2005, there were already 4 ESA PEGS calls. We applied for 4 of them. We got 3 of them. 2 were dedicated to space debris. The one is in negotiation right now and will be dedicated to Meteor project, an AMOS system. So when I talk about 70 centimeter, I will talk about astrometry, light curves, and coloring. This is programs we have there. So for astrometry, we have a limiting tracking capability. So you saw this is a typical astronomical telescope. So you cannot just set up any rates in relaxation declination direction and follow any object you want. You have some limits with tracking rates you can use. You can combine them. You can play around. So the easiest, of course, to track is geo population. Usually you just have to turn off your tracking and you're fine. The same goes for the GTOs and MONIA when they are in apogee. They are very slow, and comparing to in the topocentric system, you can track them for several seconds to have the best signal you can get from them. And then we have also LEO, but LEO at this stage is that we can only acquire a streak with the background, star background, so we can have a 1-2 points maximum per one passage of the object above your observatory. So you probably all are familiar how what is the problem with optical observations and space debris. These objects are very fast. This is similar with NIA. When you have, let's say, 60 minutes exposure, the object is several degrees per day. So it can happen that you have a streak, not a point. So this is always happen in our case. You can either have a streak, the object is as a streak. Here you can see it. GEO4 geosatellite Astra, they created a streak during 5-second exposure when we use the sidereal tracking. Or you can increase the signal of your object by following the object, but then you have a problem with stars which become streaks. So you can process this, not usually with conventional astronomical tools. That's why you have to either go for experimental ones, or you can develop your own like we did. But the problem is, even you can process it, you still have a problem. When you go for higher and higher exposure times, the stars are beginning being larger and larger, and the signal is spread over more pixels. You're losing the signal of the stars. This is especially a problem for LEO tracking, and also they're contaminating your object. So more stars, longer stars means there is higher probability that you will have less and less images when your object is not crossing the star, and you will lose the measurement point. So what we did in the previous activity, we decided that, okay, if the objects are too fast, we will go for the bright ones, of course. So when we do the validation of the system, so we follow the GPS satellite, what we do sidereal tracking, and we do very short exposure time, 0.1 second. We know that the phase angle of this object was roughly around 45 degrees, I think, so we know it should be bright enough. From the experience we observed many times. So the signal is enough. I think it was like 15 signal to noise ratio for this case, so for astrometry this is perfect. And we have enough background stars to actually perform the astrometric reduction. On the right is a different case. We have a geo object, but this is unknown one, which is even rotating. Actually, I can move it that you can see the direction. So you see, and this one is inclined orbit, probably like 7 degrees or 5-7 degrees. It's a geo object, and you see it's also rotating. So not every point you measure, you actually get this. You cannot every measure point get a point from each frame. So. For that reason, you have to acquire more images, and here will be probably the best idea to actually follow the object. But in this case, we couldn't do it because it was fast even in the geo-tracking regime. So when we do the GPS, GNSS satellites, we know their positions with accuracy of few meters or even centimeters. This is thanks to the geodetic groups which are working with the satellites. They have the solutions where they calculate the geocentric point, they calculate the GPS station exact position, And the whole product also provides you the exact position of the satellite to millimeter centimeter level. So once you use this position, you calculate them, you do prediction on ephemeridis for your observatory. You can actually confront the calculated ephemeridis with your observed data. And for this GPS, GNSS, you know that you are definitely wrong, that the calculated one is the best as you can get. So you confront this data with this ephemeridis. So we did this for like 48 nights of observations. We observed GLONASS and GPS. And our colleagues on Astronomical Institute in University in Bern, they processed this data, and they, I mean the astrometric data, and they gave us a feedback. So this is how it looked like. We're talking about 3 different time periods. One was before April 2018, one was during April 2018, and one is after April 2018. When you can see on the upper figure is the epoch bias, the shift in time that they identified in our data. On the lower figure, you can see the astrometric accuracy they could actually extract from the comparison from the residuals. And what we can see is these 3 regions. And when we talk about before April, we see this was on the epoch bias on the level of minus 30 milliseconds. Then suddenly something got terribly wrong, and we were on level of 500 milliseconds, which is crazy. It's half a second. And then we got, again, on some stable value, around 68 milliseconds. So when we look at it deeper, we find out that actually what happened here is that in this case we used commercial software, but the time precision, time tag, in the Fitzgerald header was set to 1 millisecond. This was reset once we restarted the whole system, and the commercial software, we actually forgot. The commercial software was set up for 1 second, which is sufficient for asteroid people, but not for us. And in that case, this month of data was of very pure quality. Then we moved to our own software, which is now communicating directly with the camera, directly with the mount. So we have the full control over the time tag and everything. So in this case, we still have some epoch bias, but it's a constant over time. So there can be some accumulation of the time delay, but this time delay is constant over time. And this is the important information, that even you wouldn't do the analysis between these 2 dates, you still are confident that the data are not going somewhere between minus 50 to plus 50, which is essential if you want to provide this data for orbit determination. Except this analysis, we also provided some data to Astronomical Institute concerning the orbit improvement, but this I will not report here because it will be several slides again, which I think I will not have time for. So just an example of LEO that you have kind of feeling what is happening when you do LEO. And now what we do is you can see on the left streak, which was caused by International Space Station. We use exposure time of 50 milliseconds. So this is what you get when you do LEO. Even with very short exposure times, here you even have to use the V filter to decrease the total intensity, the incoming intensity. So you have really bright object, and it's still streak. On the right, it's not very visible, but you can see very faint streak, which was acquired with exposure of 0.2 seconds. And this is a CubeSat. Slovakian one is the first satellite ever we launched, and it's not functional anymore, so it's a space debris now. And it was in the range of roughly 750 kilometers from us when we were doing this data. So you can do the astrometry, but with low, very low exposure time, you get a problem of reference stars. This was not the case here, of course, but these, for LEO objects, the sky changes rapidly, the background, so you will have spots when you cannot measure the astrometry and they can measure. So now I move to the light curves. We acquire light curves only for LEO, for GTO, eccentric orbits, and the GEO because of the tracking capability. And in the future, we will do it also for LEO, but this is not the case now. So the products we are interested in is the shape determination, attitude determination, evolution over time of the attitude, and a prediction of a fragmentation. Here is an example of series of, I think it's like 50 on 100 subframes, 256 by 256 pixels, acquired for GEO upper stage, Titan 3C. It's a pretty old lady. It's from 1974, so it's roughly 45 years old already. And we were examining the rotation properties. So here is the light curve. You can see that we were acquiring the data for more than 25 minutes, no, or 30 minutes. Yeah, it's roughly almost 30 minutes or 25 minutes. And you see that we are undersampled in this case. So it's like 5 points or 6 points per one rotation or between 2 maxima. But what we do, we actually use we use techniques like Fourier fast transformation or Lom's-Cargill to identify roughly where is the maximum, and then we do multiples or fractions of this, and by using phase dispersion minimization method, and this always leads us to, or always, it was too confident to say, but very often it leads us to very nicely shaped reconstructed phase diagrams, which is the final product you want to have. With each phase diagram, you immediately also will get the period for which you constructed it. So for this case, the rotation period was 25 seconds. The other product you can get is the amplitude of the light curve phase diagram. So in this case, it was 1.2 magnitude. There you can also investigate how many peaks there are. When we're talking about upper stages, cylindrical shape, so usually have 2 peaks and 2 minima. When you talk about spacecraft, usually have 4 when the bus and also the solar winds, solar panels are reflecting light towards you. So this is the product we do with light curves. And we actually acquired so far 285 light curves since 2017 for 226 individual objects. We constructed phase for 153 of these objects. So we have phases like this, but some of them are more dispersed because the data quality is lower, because the signal was lower. And here is roughly the distribution of rotation rates we actually were able to extract. What we find out is probably, you know, these objects can rotate from second per rotation up to hours. It depends on the type of the object, usually. We also generated an online catalog, which will be publicly available once the publication is out. It's now in preparation. So anyone who wants to actually work with this type of data will have access to it. Then we have a color photometry when we are interested in the surface properties of the object. What we do is that we use actually, we have a filter wheel with Johnson-Cousins filters, and thanks to the Landau work, we are able to convert, and thanks to the Landau standard stars, we can actually find the transformation between our instrumental system and the standard system, and this way we then can extract magnitude or brightness in different filters. In the end, we are interested in the difference between different filters, for example, blue minus visual or red minus infrared. So here is an example of a very complicated case of Falcon 9 upper stage, which is quite young, with a dominant white surface. It was observed in 2007. It was launched in 2017, I think, and we observed it. I hope I wrote it in November 2019. Probably not 19, 18. Typo. So we observed it with 4 different filters. We reconstructed the phase for each filter, but we did it simultaneously because here it's really crucial that the phase diagrams are together aligned as best as possible. Otherwise, you will get nonsense data. So here you see reconstructed phase for each of these filters and as a function of the phase. So difference between each point, for example, in 0.5, this difference is B minus V. And once we plot these differences, you see color index as a function of phase. So for some of these color indices, you see there is a trend which is following here minima, it's here maxima. It's just basically telling you I'm looking on this dominant part of the object, or I'm looking at the base or combination. So sometimes dominant is the base, sometimes is the combination in the color. So when you plot the minima and maxima, here you have a minimum 2 minima, their colors in BV and RI diagram, and here you have maxima. If you would have nicely aligned your pointing direction to the object to the rotation axis, so you have a minimum, maximum, minimum, you would expect that the maxima will be the same because you see the cross-section from this direction is the same. The difference is the basis. So there you expect the difference where we didn't see it. But the problem is that we didn't have the direction perpendicular most likely, and for that reason, these colors are combination of all these factors. So for this object, the best way to do is to observe it the whole night under different phase angles, so you see your angle between the rotation axis and you is changing, and then you can actually do much deeper analysis. But this is how the product can look like from one data set. And this is how these color indices were changing over one phase. So you see it was moving like that, and this feature is fully dependent on the shape. No, this one should not be shaped. This one should be the color itself of the material. Okay, so I see my time is running out, so I will just go briefly. To be able to process data, astrometry and photometry, you have to, as I said, you cannot use conventional software. So what do? We develop our own system. We call it image processing elements. We are focusing on having each element which is responsible for image processing independent, so we can anytime either replace it or add another one, and you can choose, if else, which one you would like to have. And then you can test them individually, but also you do full tests, which we are running right now for astrometry and photometry independently. So we have different elements like background estimation to make the whole image flat if you have a stray light or some parasitic light on your image. Centroiding and identifying object on the frame is the most crucial, right? You have to find the object as efficient as possible and have them accurate as possible measured. There is image reduction, masking, which helps you to filter, and so on. Trackhead building, quite nice mathematical problem. Then you have object identification when you combine with the catalog and some technical conversions to international standards that you can provide it to your partners. So it's just an example of background estimate. You have the signal in your frame, you calculate the background by the mathematical methods, and then you remove it and you have it nicely flat. Here you find some suspicious pixel, and then you start to getting closer, and in the end you actually set on the object and you measure the x epsilon, xy, which is the centroid position, and total intensity in the moment. So this is the centroiding part. Okay, so I go to conclusions. So focus, Argo 70 and research for space debris, they are strongly linked. So most of the development and research is for 70 centimeter telescope, which we are doing, and is usually done by is mostly done by the ISAPEX and ISA activity, so collaboration with other partners. We are planning to maintain and extend the light curve catalog, so we will still working on it because we need also data for the color photometry to perform analysis, and maybe in the future spectrometry, excuse me. This will be done by internal projects and new bachelor or master topics. We will create our own color index catalog, which we will also make publicly available. As I mentioned, we will use Johnson-Cousins filters. This is the PhD project of my student, Matěj Zigo. He will start in September this year. There will be extension to his work, most likely to adopt the system we have already to NEO objects or near asteroids. And we will have a closer look to how can we use the data from our colleagues, for example, spectra, reflecting spectra of LEO objects, which you can see quite often in AMOS cameras. So these data are quite unique, and we will have a look on them and try to link the spectra, obtained spectra with photometry, which we are doing with Argo 70. This is a diploma, master's thesis of my student, Danica Šilkova. And then we will, of course, still continue with software development for the image processing and do the validation in cooperation with the Department of Applied Informatics, where we have a really good agreement. And there we have a PhD student, Stanislav Krajčovič, who is taking care of this project. And with these references, if you're interested, I will close my talk. And if you have any attention, thank you for your attention. If you have any questions, please don't hesitate to ask. Jiří. Yeah, it's fine.
Thank you. Just a comment and a question. The comment is that in the slide where you present the AMOS, the image appearing there is not Chile, it's the Teide Observatory.
So it's not?
No.
Ah, okay.
You can see the Teide mountain behind, and the logo that appears in the lower right corner is the IAC logo.
This we have to fix because we're presenting this quite often. So which one?
No, in the previous one.
Ah.
No. There.
So this is you then? Yeah, of course.
This is Teide.
Yeah, of course. I see the mountain there. Okay, thank you. I have never been there yet, but if I would go, I would probably fix it. Thank you very much. So I will correct this.
And the question is, regarding space debris detections, how do you detect the beginning and the end of the trail? Because this is crucial for astrometric accuracy.
So what we do now is, okay, so when we have a trail, we can do with the edge detection and so on, but we don't do that. What we do is that we know a priori the information how the object was moving. We know what is the point spread function, or what is the full width of half maximum, or seeing what we had. So we know exactly the trail size. We know the length and we know the width. And we just put the box, as I showed you here, we put this box around the trail, and the box then kind of descends or kind of put itself or iterates until it is fully covering, fully covering the point, the streak, and then it measures it, this one. So you see, what is happening here is actually that this box is just traveling around, and in one moment, one condition is fulfilled, that I see something suspicious, some pixels above the background. So then it starts to move around different directions, and in one direction, it's the number of pixels which are above background increasing. So it's moving, and it's doing, all the time it's doing centroiding. And what is done is that every time you find you are in this position, for example, it will tell you, no, the centroid should be a little bit more further that direction. So you move, and again, you do centroid again, and you move again, and in the end, you iterate until you do, the difference is very small. So this is how we do it right now. We know the size of the box, and the box will just slowly iterate until it's got the best match for the centroid, and the centroid is not moving from one position to another.
And is this method working for both for GEO and LEO orbits? For
LEO is really experimental. We didn't measure yet. Maybe I was not, probably I just put you in the wrong position, thinking that I'm lying, but we didn't measure yet LEO. We have it ready, but we didn't do LEO because for LEO we have probably now like 25 streaks we can process, but we can still only confront it with the TLEs. So it's difficult to actually say, but we will do the analysis, but we don't have it yet. But the idea is to use exactly this one. But with LEO we have only one streak per object, so what would we do? We will just put the box probably on top of it and let the algorithm to do the job.
Thank you.
Any more questions?
How often do you catch a collision? Do you predict them? How often does that happen?
So you mean in general, because we don't do it yet. We are more focused on providing the service if something like that happen. But we had collisions, for example, in GEO, there used to be only 2 collisions in the whole space era, but we got like 3 explosions in the last 4 years. So in GEO is now roughly 1 explosion or fragmentation per year. On other, it's probably few. LEO is probably few. On GNSS, we don't have much explosions actually. This is very dense part. The population is very small, like 7% of whole population is there. So we don't have much fragmentations there. But the fragmentations, they can be 2, right? One is high energy, where it's probably internal, or there can be collision. Collision can be kind of identified from the orbital elements. All of them can be distinguished from the delta V actually. So, but we don't do this. We can do it. We need to know it once we want to predict, for example, do survey, right? We know there was an explosion, so we need to know where the fragments could be, where we should look to have the highest, statistically highest probability to catch some fragments.
Okay, so if there are no more questions, we should probably go on to scientific coffee, which is in the cafeteria. Okay, let's thank the speaker again.
Thank you.